Like basically everything from here, right?
Well, yeah. So it's basically kind of like inside the door. You know how he said there's like that net?
I think he basically got caught because he had an interview with Sean Penn, like undercover interview with Sean Penn. Yeah.
Then you need to start.
So that's let's know there's people in here. Say.
So Wes. I always sit here. It's my spot.
So last time we kind of got stuck in a derivation, right? That was the Gaussian maximum likelihood. I don't want to solve that in class because, as I said, it's not required for the course. But if the people who are interested in the math, we should come to office hours and figure that out. We're gonna need for that derivation matrix differentials, right? So how do you take the differential of the determinant of sigma and of sigma minus 1, things like that. So it's absolutely not required for this class, but if you are into math, we should figure that out. Back to the Gaussian itself, what do we have here? The Gaussian discriminant analysis. That says, so probability, I have a probability of y equals 0. That was this data probability of 1 to 1. V, sorry. And then I have probability of x given y is 0 is 1 over y power So I have two means. This is mean, say average. Average of data points with y equals 0. That would be the sum over all the data points xi times the predicate is yi equals 0, yes or no, divided by all of these guys who have y equals 0. The average of all the data points that have y equals 0. And the other thing, the average of data points with y equals 1, that would be the sum of all the data points, predicate is y equals 1, divided by how many things. So the variances that I have here, the sigma, could be the same sigma or different sigmas. So I think in the homework you're going to have to play with this sigma to say, do I want a different sigma for the two classes, or I want just one sigma which can be estimated from. I won't do the derivation, but we have the result for sigma, right? So sigma, so those are the maximum likelihood parameters. Sigma is 1 over the data points, number of points, class. Now you have to adapt this formula for whether you want one variance or two variances. If it's two variances, you have a sigma 0 and sigma 1. So sigma 0 will be over only the points that have y equals 0, and the mean will be y equals 0. If you have, and then sigma 1 will be the scatter matrix, how it's called, or the empirical covariance matrix of the points that have y equal 1. If you want to do it together, it's get one sigma, and then that's good for both classes. The practice, the engineering, would be like you have to use the right mu for every x. So if this x has the y equal 1, when you sum up here, you're going to use the mu for the 1 class. And for x's that have y equals 0, you're going to use the mu for the y equals 0 class. The means are always different. More conceptually, if I impose the same variance for both classes, the Gaussians will look the same. They will just be in different places, right? The Gaussian has a mean that's the center of the Gaussian. The centers are different. There will be a center for the positive class and a center for the negative class. But they will look the same as shape if they have the same sigma, right? So if you look at the Gaussian from the top, so these Gaussians, let's say I have two axes. I have two features, x1 and x2, right? So x is x1, x2. And I'm looking at the two classes from the top. The Gaussian sits on the plane and pops out of the board in terms of the frequency, the height of the Gaussian, right? So if I look here, I'm going to see maybe here's a Gaussian. This is the Gaussian. The base of the Gaussian, right? And it's coming out of the board. The belt is coming out of the board. And maybe this Gaussian again, and it comes out of the board. So that's if instead of looking at the Gaussians on a plane and they have nice belts, I'm looking from the top at this plane, and the belts are coming at me. Right? If I'm looking from the top, what I see is the contour of the Gaussian. There's not really a contour because Gaussian extends to infinity, right? The Gaussians have no end. They get very, very close to the x-axis, but they never touch the x-axis. But assuming at some point we say we terminate them, we're going to see something like this. And these are different sigmas or the same sigma? This will be different sigma. So this is the center mu 0, and there's a sigma 0 here, and there's a center here mu 1 and a sigma 1. If I impose the same sigma, I'm going to have two exact same Gaussians except a different center. The center is always right. Make sense? So I really want to do that derivation, but not in class. So for today at office hours and maybe Monday or Wednesday next week, the people anybody work out that math or at least attempted to? You found one problem. There's a d that I put on the board that's definitely an n. Let's do the sum. But then did you find the formula for the sigma minus 1 inverse? Okay. So somebody worked it out. How about you?
Yeah, I did that.
Did it work?
Yeah.
All right. So just come to show it to me at office hours, and then maybe one of you can write it very nicely and put it on Piazza for everybody to see. Huh?
He already did it.
He did it? You put it on Piazza? Good. Okay. So I think it's a good exercise. Even if you are not a mathematician and you don't want to be a mathematician, I think it takes the time to say, okay, how do the people do these things? Because here's what I said last time is the 3 levels of machine learning. The basic machine learning, I've heard of that, but I have no clue how it works. Right? You don't want to be at that level. That's too low. That was good 20 years ago, but now it's not enough. There's the level of, okay, I went to the textbook, I went to the class, and I understood the derivation, and I implemented the code. That's your goal. And there is the level of, I want to do a PhD, So I want to be able to get through this math, not just to get through this math, but to do it my own. If I tell you here's the maximum likelihood, derive it yourself. That's what Ketchen did with your neural network that was the maximum likelihood network. He took that network and differentiated to give you the formulas. Right? So I think it's a good exercise to try to do this, at least the middle one, to say if somebody shows me a derivation, can I work it through? Can I do step by step what it is? But not required. So now I want to understand a little bit how this sigma plays out. So in this case, I have x1 and x2. Sigma, I'm going to ignore this drawing, but I'm going to do a different drawing here. Sigma is what? Sigma 1, 1, sigma 2, 2. That's a matrix. This is sigma 1, 2, sigma 2, 1. So I have some questions about this sigma. We already said that sigma 1, 1 and sigma 2, 2 are what? Who's sigma 1, 1? I mean, if you should write it as squares to be you know, like notation from unidimensional. That is the variance of x1, the column 1 in the data. So it's the variance of the first feature value. And sigma 2, 2 is the variance of the x2. So what I wonder is how is this Gaussian looks for different matrices. So again, I'm looking at the Gaussian from the top. So I'd say here's an example. Sigma is a basic 1, 1, 0, 0. If I am to plot that Gaussian, the center is somewhere, right? This is x1, x2. I have a center, doesn't matter where the center is, that's the mean of the Gaussian. How is it going to look when I look at it from the top and I look at this Gaussian, the bell is coming at me, it's like a pointy thing at me, and then it goes down. How is it going to look if I say, okay, whatever is very close to the plane, I cut it? How is it going to look? Okay, you guys follow me? I have this variance matrix, the sigma matrix. I plot this Gaussian, and I'm looking at it from the top, and I ignore the height. The height is the Gaussian height. But what am I going to see in the basic plane?
Oh, a circle?
I'm going to see a circle. Okay. Nice. What if, let's do another example. My sigma here is, say, 1, 4, 0, 0. What am I going to see? So this is x1, that's x2. There's a center of the Gaussian, which I'm going to ignore for now, what it is. This is going to be a circle?
No.
No. It has more variance on which dimension? X2. And now the variance means what? The more variance it is, the Gaussian is more tight or more loose?
More loose.
More loose. So how is this going to look?
It will expand towards x2.
It expands on an x2 axis. Right, so it's going to look like this. More wide on x2 because it has more variance, but more tight on x1. All right? What if I start having 1, 4, 0.5, 0.5? We said mysterically, like, those non-diagonal values correspond to what? Correlations or covariances or some sort of relation between the features. We're going to get there. I want you guys for now to keep it at the common sense. If I have 0 means independent features. If I have non-zero means there's some relationship between them. What's going to happen to this Gaussian? How is it going to look? It's going to tilt a little bit, right? I don't know which way, to be honest with you, but I know it's going to tilt. It's going to tilt that way or this way. Well, I don't know. Wait, I think it's going to look like this. Something like this. I don't know. I have some plots in my notes of this, but the best thing to try this would be to use a program like MATLAB or Mathematica or something very mathematical, plug it in. You know, you can plug any sigma you want in there, and the program will plot it for you, and then you can take a look at it. MATLAB does it 3D, so it's very easy to rotate that plane. If we have some time, maybe we can do that together. So I think it's very important right now, since this is maybe the first exposure to have to those models. By these models, I mean multidimensional Gaussians. I know most of you have seen a Gaussian before, but I think most of you did not see a multidimensional Gaussian. That is, the base of the Gaussian, it's not 1x, but it's x1, x2, x3, x4, and x5, or x20 or 50. And the height is still unidimensional, right? The height in any x Gaussian gives me some frequency value. So that is how it pops up out of the board. That's still the value, the frequency, one dimension. I think it's critical to take some time to just think and look at those Gaussian to understand what they mean, multidimensional Gaussian fits. Because they have a strong shape assumption. In reality, like I said, no data is going to be Gaussian. But it does not require this independence assumption. As you can tell, if I play with that matrix sigma, I could get to all kinds of dependencies between my features. So in principle, I could model complicated dependency as long as my data looks roughly, if you have to think of a Gaussian in common sense, there is a center where typical values are. Take student ages. There is a center, right? Students are about 20 years old, right? Not master students, the undergraduate students, 20 years old. So there is a center where typical data is. And as far as you go from the center, it kind of drops off, right? So most of the frequent values will be at the center. Most of the students will be about 20 years old. And as you move away from the center, 21, 22, 23, you see less and less students with that age. Even if the dropout is not governed by the exponential square function, this is an exponential squared, right? Like a squared inside the exponential. So even if my data looks like I have a center, and the dropout is not exponential, or it's not exponential of the x squared. Say from here it goes like this, and from here it goes like that. That's okay. All these kind of things can be approximated very well with Gaussians. Remember, what's the condition to match with the Gaussians? There gotta be a center where most of the data is. And as you move away from the center, the frequency has to decrease. It doesn't have to be a nice, smooth exponential function. It could be, maybe it decreases like this. Maybe this one is very steep and then flat and then steep again. That's okay. As long as you have this critical normal property, moving away from the center, frequency starts decreasing, which is a very natural property. It happens a lot. You can model it with the Gaussian. So you don't have to worry on the Gaussian, okay, is it really AE at x squared or minus x squared? That's a dropout of a Gaussian function. What you have to worry is if I have multiple peaks. There's some data that doesn't have one center but has two centers. There's two kinds of patients, two typical patients. There's this typical patient here, this typical patient here. I have high frequencies in here, high frequencies in here, and something else in between. That sort of thing cannot be modeled well by a Gaussian. So again, we don't worry about how the dropout look like because that's going to be okay. What we worry about is a typical spike and then moving away. So now, I don't think we have to recap the plan. The GTA plan was, we have these things. That's for 2 classes. But if we have 3 classes, we'll have 3 of them, 4 of them, 5 of them. How many classes we have? We have 18. We can have 18 of them, right? And then once the training consists in what in here? The result of training is to produce the parameters, mu, sigmas, whatever I have. For your homework, I would like you to try different sigmas versus 1 sigma to see how that makes a difference. And then in testing, what do I have? I compute P of, for a given data point X. I do P of X given Y, right? From there, actually I want P of Y 0, Y equals 0 given X. Is P of X given Y 0 times P of Y 0 divided by P of X, and then P of Y equal 1 given X, P of X given Y equal 1 times P of Y equal 1 divided by P of X. And I say whichever one is bigger, I'm going to predict that class. That will be unnormalized. If I don't really bother to compute P of X, then I get an unnormalized probability. If I want the exact probability, I have to deal with this P of X. I would have to have the priors, P of Y0 and P of Y1, which I can compute from the training set as a frequency of what percentage of data points have Y equal 1 to start. And this is what I get from the models. This P of X, Y equals 0, I have the X, I plug it in this model, I literally plug X in here, do the calculation, I get that P of X given Y equals 0, I do the same for the other one. That's the discriminant part, where I compute the two scores and I pick the one that's bigger. Final thing about GDA, I don't have to use Gaussian functions here, right? I could do the same pipeline for any sort of modeling. Suppose I want to use a Poisson distribution or exponential distribution or a beta distribution. Because I believe it models my data better. Beta distribution can model the two spikes, for example, right? Which, if I believe my data looks like that, I know the Gaussian not going to fit it, no matter how hard I try. Because I Gaussian model one spike and I have two spikes in my data. So maybe I choose a distribution that allows me to have two spikes. Still, I want a nice function to do the math. Then I have to fit in there that beta distribution, compute the beta distribution parameters, the two parameters in that distribution. And I can do the same thing for testing. I can compute the probability of coming from that class or that class, whichever one is bigger, I output. Right? So the discriminant analysis, probabilistic discriminant analysis, doesn't have to be Gaussian. I can fit whatever model I think fits my data well. Now, Gaussians are easier models to fit, because you just have to compute means and variances. The harder this distribution gets, gamma, beta distribution, so on and so forth, they become harder and harder to fit well. But latest versions of MATLAB and Mathematica do quite well at fitting curves. So if you don't want to, the homework, it's easy, because if you skip the derivation, what do you have to do? You just have to compute this and that. That's the training. That's extremely easy because we allow you to use mathematical functions to do so. So you don't have to compute this sum manually. You can just say, give me the covariance of the data. The hard part, it's going to be this. In a test, when you compute this value, you're going to have to deal with this sigma and minus 1. The easy part here is to call MATLAB and say, I have a data point X. Can you give me the value for that X? You know, because MATLAB has an approximation to do it internally somehow. But in general, this is the hard part right here. When you get a data point, how do you do this? It's not just the computation part, it's the stability part too. This B sigma being a matrix 50 by 50 or bigger could be computationally difficult. So in practice, what people do, I think I said this before, if I take the sigma before inverting it, because I need sigma minus 1, if I make the diagonal a little higher, the main diagonal as you see it, then inverting is a more stable operation. The higher the diagonal, the easiest to invert, because the inverse of a small elements on the diagonal is going to create large elements in the inverse. So that's something that we're going to have to play with it back and forth to see what you guys get. There's a question? Okay, hands up who's with me so far. Good. So now what? We have this, we're done. That's your homework. But I want to do, since we talked about Gaussians for 2 days, I want to do some side conversations about those Gaussians. That's what I'm going to do today. And I think that's pretty much enough for your homework. The homework that's coming next week. I'm going to try to post this homework tomorrow, because if some of you finish the neural networks or give up on Don't do that. If you do, you have something to move on, right? Because a long weekend, we don't want people to have a long weekend with nothing to do. So let's try to pose that earlier. So I don't really want to do that much of clustering, but this discussion starts with clustering, and I'm sure you heard of k-means, right? Let's do a quick recap of k-means. Although, like I said, k-means is not my interest right now. Let's see quickly what is k-means. So I have a bunch of points, right? I'm going to say, here's the points that's being grouped, these points. They belong to this center, they are closest to that center than to other centers. There is another center here, all those are stars, so they belong to and all these are, say, minuses. I'm going to call this one mu1, mu2, mu3. The idea is every data point has a membership value. I'm going to say, so for data point xi, I have zik is membership on cluster k. So in other words, this is 1 if xi belongs to cluster k, and 0 if xi does not belong to cluster. So all these points in here, they're going to have zi3 equal 1, and zi1 and zi2 equal 0. Those are called membership variables. So all those points here, all these xi here will have zi2 equal 1, zi1 equals 0, zi3 equals 0, right? Because all these memberships belong to the second cluster. Everybody here is going to have zi3 equal 1, and everybody here is going to have zi1 equal 1. Okay? So zik is the membership of data point I into the cluster k. It's 1 only for that k that the point belongs to, and 0 for the rest. So zik is the purpose of k-means, right? At the end of the k-means algorithm, in k-means you have to supply the number of clusters you want, right? You have to tell it, I want 4 clusters, 5 clusters, 6 clusters, right? So we have this global variable k, which is the number of clusters. This will be C1, C2, Ck, small k, up to Cbk. And k is this indicator of which cluster the data point belongs to. This is what we want to get out of k-means. So k-means produces two things. Produces the zik values, and what else it produces? So as an input, I get the data points xi. I get labels in k-means? No labels. So no, there's no yi there. But what else do I get? I get the big K, right? So this number of clusters. I apply k-means, what do I get? The memberships, which point belongs to which cluster. What else?
Centroid.
The centroids. This is the center of cluster K. Right? Exactly what is the center of a cluster? Like, what's the formula for the center? How do we write that? Is sum over all the data points, average of them. It's like before, is that average? Average of the data points with the predicate Zik equal 1. So I'm only summing up the ones that belong to that cluster, divided by the sum of how many things have Zik equal 1. Their average. That's it. That's k-means. Did you ever see k-means taught that fast? Well, that's the output, but how does it get there? Like that's what we want. We want to partition those points. Oh, there's another property. How do we determine a point belongs to a cluster? Zik is 1 if k is the argmin of the distance between x and so a point xi and mu k, right? So I go through all the centroids, I measure the distance to the centroids, and I pick the k that has the minimum distance.
When you say distance, would that be like the Euclidean norm of the difference between the point and the...
I want to leave it generic for now. I think you can implement different distances. Be careful between similarities and distances. If you use a similarity like cosine or dot product, you got to be 1 over that or some formula like this. So I want to leave it generic. I think the default distance is the Euclidean distance. That is sum of the xi squared minus mu I squared overall, but people use all kinds of distances, right? I'm not too worried about that. But that's essential. The point belongs to the closest centroid. So how does k-mean does this? How does it just get a bunch of points and a bunch of the number of clusters? And how does it produce this? So this is kind of the result in here, right? Because I don't know who belongs to who, and I don't have the centroids. That's the result of k-means. So how does it do it? I don't want to do the exact details of k-means, just in principle, what's the main thing? I can imagine that I start somewhere, initialize those centroids with some values, for example, and I put the points closer to whatever centroid they are, and then what? Recalculate the centroids, and then so I think as a plan, as a outline, start with some initial mu 0, mu 1, mu k, right? Maybe random, maybe not random. Furthest far traversals kind of things, who knows? Some good centroids. Then what? Loop, right? There is a loop in here. So the loop is first how do I assign the points? We use this formula, right? We use Zik, the membership is going to be the argmin. Maybe I should also design a function, right? What is the distance? I have to figure out what distance I want to have between any point and the centroid, right? Like maybe I use Euclidean distance, maybe decide some other distance. But that's fixed. I can compute those distances in advance. I mean, I can't compute in advance because the mu's are moving. Sometimes they're not moving really, so there's a way to cache these things, but that's engineering detail for now. Let's say I can just compute the distance everywhere. It's argmin over, that's k. K I mean over all possible k primes of the distance between xi and mu k prime, right? And I say compute this k, I say Zik equal 1, right? That has to be for every I. For every data point, I figure out which one is the closest centroid, I make that Zik equal 1. And all the other Ziks, not k, is 0. Every other centroid is 0, so those are membership variables. And then That's step number 1.
Update the views.
Update the mu. So then every mu k becomes that formula, right? So I kind of already wrote the algorithm right here. That would be the average of the data points with zik equal 1, right? That belong to that cluster. So that again is that formula there, sum of xi, zik equal 1, divided by sum of zik. Good. Now, see, this is a loop with 2 steps, right? I'm gonna call this, I'm gonna give him some name, okay? Just for the purpose of reference. I'm gonna call this one the E step, and this one the M step. So it's a back and forth, do that, then do this, then do that, then do this. Why is this necessary? Like, why can't I do like before, right? I can instead of doing this, I could in principle come up with a likelihood function, right? You could do that. That it's dependent on both zik and mu k's, right? And then take that objective or likelihood, differentiate it, and set it to 0 to say the parameters I'm trying to get out of here are the mu k's and zik k's, right? That's what I'm trying to get out. I can determine some sort of objective, gigantic objective, and say minimize or maximize this objective. That's my plan. Differentiate that objective in terms of zik and mu k and so on and so forth. And then set it to 0, right? And that will be some solution of this. Why is that not working? Why is not that easy? I don't know. Yes?
Are we being given unlabeled data and trying to find
Yes.
clusters in it? So
Unlabeled data.
what would your objective be? It can't be based on accuracy of predictions.
Right. So let's say what would be a reasonable objective here?
Reduce the mean.
Say reduce the minimum, the average distance or the sum distances between the points and the centers, maybe. So that would be, well, how do I write that? The sum for every data point of distance between xi.
And give it corresponds to I.
Right, that is mu ik, and I can multiply this with zik, right? Because only the zik equal 1 will matter. If zik equals 0, won't affect anything in here, right? So I have all data points or centroids, but only the distances that matter there. So I want to minimize these distances. This is a well-defined problem if the number of centroids is fixed. It's not well-defined if k is not fixed. I can obviously minimize the distances with more centroids, right? If I have a lot of centroids, I get the centroid close to every point, all distances become 0, and then I don't have to nothing. But if I say k is 5, and I have 1,000 data points, this is a well-defined problem. So can I, yes?
But for every point, you could have one of the k labels. Right, so you have to.
There's no labels.
For every, at each point, you have zik equals 1 for all of it.
You have zik equal 1 for 1k.
Right, so if you're thinking about all the possible ways to assign one specific k for each point, then there's every single point has k of them. So the total number of possibilities for ways to set k for every one data set is exponential.
Right. So he points out the complexity thing. There's a lot of zik's in there. I don't think it's exponential. I think it's how many data points I have, 1,000, times how many centroids I have, which k is given to me is 10 or 20. Right? And I have to figure out for each point, one of the z's have to be 1. The other ones have to be 0. But why can't I just do this, right? I can do this only if I know No, k is fixed, I know k, but this step in here, just going to, this is an integer programming problem. Set up which data point gets which cluster to be 1, which Zik is 1. I could do this in this with this formula here if I know the centroids. But the centroids are variables too, right? I could do the other thing, I can easily compute the centroids if I know the membership. If the points come with labels, if somebody tells me, hey, all those points are blue, all those points are green, they belong to the same cluster, and all those points are yellow, I could easily average them, get the centroid for each one of them, right? Hands up, who's with me? Every one of these steps is easy in itself. Why can't I write this objective and differentiate it by Zik and be done with it? Set it to 0. Well, I don't have the differentials, but my guess is when I take the differential with respect to Zik, there will be all kinds of mu's and other Ci's in that differential. Right? So I take a differential, it's not clean like before, setting it to 0, fine, gives me an answer. I take differential with respect to mu, I get other mu's and Zik's in that differential. So I have now a gigantic system of equations that all have to be 0 that I have to solve. I don't think that's easy at all. That's the problem here. You could try this, try that objective, differentiate it, and see what happens. Now, but do we agree that every one of these steps is easy in itself? So this is a very well-known approximation in a lot of optimization problems. If you want to optimize both Zi and mu k, Zik and mu k, do it little by little. Like coordinate descent or coordinate ascent. That in general, that technique said, okay, you have many variables to optimize here. Say you want to minimize this, right? This overall distance. What I could do is to fix some of them and minimize for the others. And I'll fix the other, minimize for the ones I said the first time, right? And then alternating, hoping that little by little, my objective is going to keep decreasing until it gets the minimum. Does it make sense? So instead of doing it all at once, I do it little by little. I can't modify all variables like we did in regression. Those coefficients, when we updated the coefficients, we updated all of them. In here, what I'm going to do is keep some fixed in place. Like in here, I'm going to keep the mu's fixed. Just update the z's. And then here I kept the z's fixed, just update the mu's. And I'm hoping that little by little, if I converge to somewhere, that's going to be the optimal. If I get to a point where mu's don't change and z's don't change, right? Meaning I recompute z's, I get the same values that I have. I recompute mu's, I get the same values that I have. Then I'm calling that a local optima. And it's true, it's got to be a local optima. So if I look at this distance function might look like this. What I want is really this value here, the minimum. But I may end up here or here depending on where I start. Because all these algorithms, just like differentials, cannot produce guaranteed the global optima. All these constraint optimization algorithms will produce some optimum or converge to some local optimum. But once I'm in here, once all the derivatives are 0, means if I run on updates, I don't improve anything. So I have no way to get out of here with this algorithm. Okay. So there's few points in here, some new, some old. One thing is, I moved it into non-labeled data. That's not what I want, but just for the purpose of illustration. I don't have labels. If I have labels and I know this is one class and one class, that's done. I don't have to worry about z's because I know the z's. I just have to compute the center. The second thing is that the differentials here are too hard to do. It's much easier to do step by step. Fix some variables, update the others. Now fix these ones, update these ones, and keep alternating until I get to some convergence. And thirdly, which is an observation about k-means that maybe you've seen already, this works really well if my groups, the natural groups in data, tend to be globular, like nice groups. It doesn't work when my data doesn't have this ball kind of shape. Because all k-means is going to do is going to create, even if he gets the right centroid, which is not guaranteed, but suppose he gets the right centroid, you're not going to be able to group around the centroid stuff that doesn't look like a ball. Suppose my data looks like this. I have something here, and some other group in here, and some other group in here, like that. K-means will not be able to do this well. Because it's gonna, whatever the centroid gets assigned, the shape around the centroid has to be some sort of ball or oval or something like this. Now, I want to map this concept of I want a ball around the center to the concept of what the Gaussian is. So what's the analogy? What did we say? When do Gaussians work well? I want to roll back 10 minutes. There is a center, and that's where most of the data is. And as I move away from the center, there's less and less data, right? Again, I'm not worried about how exactly the decline goes, whether it's a stair, or it's a flat, or it's e at minus x squared, whatever. I care about this property. Moving away from the center decreases the frequency. I say that's the same property that k-means needs. K-means needs to have not just one center, it could be 3 centers, right, or 5. But for every center for k-means to work, it needs to have this property that the data that belongs to that cluster naturally has to be more likely or more frequent when it gets close to the center. That's what creates a ball in the data. If I have other kind of shapes, k-means won't work. Okay, so what I want now is to say, I want to do a probabilistic version of k-means. So that's what I really want to do today, but I needed k-means for illustration. So it has 2 names. I'm going to say soft k-means. That's the same as probabilities k-means. That's the same as Gaussian mixture. That's what we want to do today. So our main objective is to make Zik, which in here is a deterministic 1 or 0. Zik belongs to that cluster or that cluster or that cluster. So Zik has one of them is 1, and the rest of them are 0. Right? We want to make this a probability. So we want to do the same thing, but Zik, instead of being hard 1, 0, black or white, now it's going to be what? Probability that xi belongs to cluster k. So it's not the 1, 0 thing anymore. Yes?
For all clusters.
Right, for any I and any k. So it's a probability, that's a number between 0, 1. And there's a sum that has to work out. Instead of the condition, one of them has to be 1 and all the other ones have to be 0. Now we have for any particular data point, the sum over Zik's have to be 1. Because the probability of belonging to that cluster, that cluster, that cluster, that cluster, they have to sum to 1, because it has to belong to one of them. Now, this Zik is a random variable. So that's informal. What I really want is Zik to be a random variable, and probability of Zik equal 1 is probability that xi belongs to cluster k. So Zik itself, let me delete this because mathematically it's incorrect. If somebody watches this video later, this guy knows no math, right? Zik remains a random variable. It's still 1 or 0. But we don't know if it's 1 or 0. All we have about Zik is a probability. We know the probability of being 1 or 0, but we don't know if it's which value it is. In here, we know deterministically, right? After every iteration of this loop, we know exactly which Zik is 1 and which Zik is 0. In here, we're not going to know that. We're only going to have probabilities. So how is this going to work? Let's think a little bit about what we want to do, and then we can figure this out. So suppose I have those 3 classes, right? I'm going to draw it on find some quantities first. How is this going to look like visually? Suppose I have three Gaussians, three clusters, right? And this is a 2-dimensional data, right? Every point has an x1 and an x2. That's what it is. I'm going to write this x1 and x2 in here. X is x1, x2 space. So for a moment, you have to imagine this line is actually a plane. And I have 3 means, right? And what I want to do is express the cluster as a Gaussian. Remember, my cluster is not deterministic now. It's based on probabilities. So what I'm going to say is I have some Gaussian here. It's not exact. Gaussian here. And some Gaussian here. So again, this space being x1 and x2, I have those mu1, mu2, and mu3s Gaussians. I have 3 probability density functions here, right? So each one of them, what is this one here, this line? It's probability of any feature, right? Any distribution is the probability of seeing some particular value on the x-axis. That's a 2 thing. So in here, it's a data point x that has an x1 and x2. Is what? So that's going to be a multi-dimensional Gaussian, right? Some sigma. Let's say this is sigma 1 here. I think I need a sigma minus 1 here. So this is P1. This is the probability on this curve. So I have similarly in here, this is another probability, that's a P2 of X. And this is P3 of X. So I model this P1, P2, and P3 with Gaussian functions. That's why they look like Gaussians. So now I have a data point, say it's in here, right? This data point in here has a certain probability, right? This is the probability that this point is coming from the first Gaussian. And there is another probability that's coming from the second Gaussian. And there is, of course, a very, very small probability that's coming from the third Gaussian. So I'm looking at a point. It's not 1 or 0. It's either from here or from here or from here. And how do I resolve this? Yes?
I just have a question. If these are all Gaussians, they all have different maximums. When you have to weight each one based on the number, because based on the formula you're giving, each one would have the same maximum height, right?
So let me see if I understand this correctly. The plane is the space of the data points at the x's, right? X1 and x2. The height of Gaussian is like unidimensional. They don't have all the same height, right? I can have, in unidimensional, I can have one very spiky Gaussian and one very...
The area underneath must be the same.
Area underneath has to be 1, is the integral. Any density function has area 1.
Right.
If it's more skewed, it has more of a spike. I think that's the same in here. The Gaussians themselves, the only difference is they don't sit on a unidimensional plane. They sit on a 2-dimensional, 3-dimensional, 50-dimensional, whatever the dimensionality of my data is. Okay? So what I want is to write the probability of x of a point in general as sum from k equal 1 to big K of pi k, the probability, so that's the normal density function. Of the point x, E1, E, L by E. So this is the n normal of x given mu2 and sigma. So this is called a mixture of Gaussian distributions because the probability of seeing a point, it's not one Gaussian, it's a combination of Gaussians. Right? This is each density function, and this is the mixture coefficient. There is a mixture coefficient for each distribution in there. If I have 3 distributions, I have pi1, pi2, and pi3. So this is a linear combination of the Gaussians. And we can easily check a linear combination of Gaussians will be a distribution. For this to be a valid distribution or density function, I need what? If I combine a bunch of functions that are distributions and I want to make a distribution out of them linearly, what needs to happen with the coefficients?
They should sum to 1.
The coefficients will sum to 1. Now, notice that, just to give you a sense of where I'm going with this, a mixture doesn't have one spike, right? So if I could replace in my GDA or whatever I'm doing when I model data, I say, why is it that I don't like Gaussian? What reason can I have that Gaussians, I don't think Gaussians fit to my data? The reason is the multiple spikes, informally speaking. Well, if I could replace the one Gaussian with a mixture of Gaussians, much harder to estimate, definitely. But if I could do that, I could match the data much better, right? Suppose I have 3 types of patients now, or 4 types of patients, or whatever, if I could match this distribution in my data, not just in GDA, in any probabilistic problem that I have. Gaussians will always have this limitation of you have to have one spike. If the data has another spike, more or less, Gaussians won't fit very well. But if I could do this instead, I could almost prove I can get arbitrary a good match, right? If I add enough spikes to this data and I feed it well, I could match almost any distribution of the data. So that's what I want to do. That's why I'm insisting on this, because I would like to see if I don't match Gaussians, can I do something about it? So the answer is have a mixture of Gaussians that fits to the data. So remember that we fit a Gaussian per class, right? That's what we did in GDA. In that sense, when we fit the Gaussian, we didn't have labels, right? Because we fit it for one class. So we pick all the data points that have red, and we fit it for that class. That's why this thing applies in this problem here, fitting. I don't have labels. I already isolated the points I want to fit my distribution to, just like in GDA. The only thing is, instead of one Gaussian, I want to fit a mixture because I have much more ability in distribution. But the procedure of doing this, I want you to think of k-means. When I actually do this, I want to have in mind at all times k-means, because this is very similar with k-means in principle. So what are the things that I need here? At the end of this whole thing, what are my parameters? I have two sets of parameters.
Gaussian parameter and the mixture.
I have the pi k, the mixture coefficients, the mu k's, and the sigma k's, right? And then I have zik, the memberships, right? Remember? I still have a zik, it's just not a 0-1 thing. Zik is a random variable, so I need to have probability of zik. Now that is going to be a distribution for every point, because for every point I'm going to have a bunch of probabilities on each cluster, and they're going to sum to 1. So if I look at k-means here, can I kind of do this? Can I do some sort of iteration? I would like to say, on one step, compute, assuming I have the zik's or the probabilities of zik's. Again, zik's, I'm never going to have zik exact. It's a random variable. I can't know for sure zik is equal 1 or 0 or 2 or whatever class that is. But I'll have probabilities. I think the probabilities will have to be this. Right? This is 3 probabilities right here, 1, 2, and 3. This is the probability of this data point coming from that Gaussian. So this, how do I write this? This one here is the probability of Zi, this is the second Gaussian, right? This one here is the probability of Zi3 equal 1. And this one here, this is Zi1. And this one, the big one, is the probability of Zi2 equal 1. The distance from here to this Gaussian is the probability of that big one. So how would I do this to get this working? I need to do these kind of steps, but in a slightly different way. Which one seems easier to do? The M step? But in M step, I don't just have mu's, right? What's the thing in here?
You have to add sigma, but you just calculate this, the covariance matrix for all of the x's with CIK.
Right, so before I go there, if this is a particular case of that problem, what's up with the pi I case? I mean, how can I make this look like that? Do I have variances here? Can I count some variances that will give me exactly this?
If your variance is 0, then you just have individual points like centroids. But
0?
the-
So it's very spiky. The variance 0 means all the Gaussians are extremely spiky. So what happens if I have a point in here?
It's whichever it's closest to. The probability is almost 0.
That all problems will be almost 0 in there, right? I'm trying to figure out how is this in here going to match what I'm doing there. I think we already know that I'm not just going to have the means. I'm going to also have the variances and the pi k combinations, right? Yes.
Why can't we just take xi minus the distance, like the location of the centroid as variance?
What? Xi?
So there
This
is a-
distance.
Yeah, that is the variance.
But that's just not for, that's for one point, right? If I have a xi.
Some rate over there.
Right, something like that. So if I look at this and say, can I compute a variance at the end of this process? I could, right? I could say, here's all the points in here. I measure the distance to the mean. I square it because the variance is expected as distance square. And I say the variance of this Gaussian is that. I think if I really want to, I could really put it here once I have exact memberships, that thing, right? So I think so far, the ZI case will be extremely skewed variables in this case. Instead of being random variables, the ZI case have one probability of almost 1 or 1, and the other one 0. Right? So they're not random anymore. And I could add the variances, which by the way, it's a good idea when you do k-means to compute the variances anyway, even though if you don't need them, because that will tell you something about the data. So the variance sigma k will be who? The variance of all the points that have the property zik equal 1. Take all those points and just compute their variance against the mean, right? Against their mean. So back to this. How do I write this? I have some formulas here. So let's try to start with the M step. In M step, what do I have? I have the ZIK, right? In here. In here, I don't really have ZIK. In here, I have the, in my notes, I have the expected value. So I say ZIK. Make sure I get this right. Why expectation? Let's write it this way, see what happens. Hmm? Right, I think pi k, well, we have to get going there a little bit later. Pi k are the probability of ZIK equal 1 in general, meaning without respect to xi. And zik, probability zik is for a given xi. So there's two notions of probabilities or expectations here. Is that for a given I data point, what's the probability that that data point comes from that cluster? That's what I've done here. For a given I, that's the probability. And there is another probability that, in general, not with respect to an xi, but just in general, what's the probability of coming from that cluster? That's more like the mass. Somebody asked this. This is the cluster K mass. And this analogy, who's pi k in here? In the discrete version. Pi k would be what? If it's the probability of some point, any point belonging to that cluster. How do I write that here? So who's pi k in here? In this discrete version.
Is it the number of points that are closest to each point?
Not the number, the proportion. Proportion of points in cluster K. So pi k is kind of the size of the cluster. That's how we typically see it in KB. It's how many points got in there, but it's proportional to the total. It's a fraction, right? That's the pi k in here. This is the same pi k. So here's I have a formula. Let's see if it makes sense. It says the mu k is sum over the data points of zik times xi divided by sum over all the data points of zik. That makes sense? So first of all, does it look very close to this one here?
Yeah.
Looks extremely close. It's like this one. Second of all, probabilistically, what is this? If the zik are not 0, 1, but they are like weights or probabilities, what is this? A weighted average, right? It's weighting, it's averaging all the points to get the mean. It's not just those ones, it's averaging everything. But every point is weighted with what? With the probability of belonging to that cluster. So this point will have a very high probability belonging here, while this point will have a very low probability, or this one a very low probability. Typically Gaussians go off, at some point they go very off, like the probabilities become close to zero. So I think this makes a lot of sense, both mechanically, looking at this formula, it's exactly that formula, but also as a weighted average, right? I'm averaging now everyone, just weighted with how close they are to that point. Question? Who's with me so far? Questions? Well, how about the variance? What do you think this is going to be? Try this out. So this is a sum. Is this a weighted formula for covariance? Oh, well, in here, what would be the variance? This variance, sigma k, this would be what in this case? It's the covariance matrix only applied to the points in that cluster. So that I could write this as sum over all data points, right? How do I write that? Xi minus their mean times xi minus their mean. But now I only want to do the points that are belonging to that cluster, not all of them. So I put the predicate zik equal 1, right? I only want to sum up the ones from that cluster. And when I divide, you're supposed to divide the variance with how many things you sum up. The number of things I sum up is the how many things belong to that cluster, right? This is the how many things are in the cluster. This is summing up the covariance sum only for the points from that cluster. Now this looks exactly like that, except now these 0, 1 things are not 0, 1. They're random variables, and those are probabilities of being 0, 1. But it also makes sense as a weighted formula, right? It's still a covariance sum. It's just everybody's weighted with the probability of participating to that covariance. If it's very far away from that center, it will participate nothing. Both the numerator and the denominator will be very small things. If a point is very close to that center, will participate a lot. And what else we have to do? We have to do the pi I case, right? The mixture coefficients, the size of the cluster. There's the analogy to the size from there, yes.
But you said it doesn't depend on xi, so do we do it as we do step by step and do this, or do we just do it in that?
What do you mean doesn't depend on xi?
Just do it in general without the dependency on xi.
dzik?
No, the pi k. I was talking the pi k.
Right, so we have to do pi k, right?
So do we do it here, or do we just do it in the end after getting a concrete mu k and sigma k?
No, but when we do it, what I mean here, it's not for a particular xi. Of course, it depends on xi on all of them as a formula. What I say here, zik is with respect to probability with a given xi. Pi k is the general size of the cluster. It's not with respect to a particular data point. So these are both probability of zik equal 1, but this is for a given xi. What is the chance that this student is in that class? And this is how many students are in that class. So for pi k, I have the following formula. Sum over the data points of zik divided by all of them. That, so what would be the pi k here? The size of the cluster. What is this? How do you sum up the cluster?
It'd be the sum
The proportion, sorry. With the sum over all the data points,
of zik.
zik equal 1, right? Divided by how many data points are there. Because that's going to sum up exactly how many points are in that cluster. And that became here a probabilistic formula. Right? And it's correct because the sum of all these ziks, they sum to n eventually, right? If for every point of sum of ziks has to be 1, if I sum over all the points, I get n, because there's n points, n by n divided the sum of all this, right? This will imply that the sum of pik's is 1, because if you do the calculations, the sum of pik's over k is the sum over k of sum over I of zik divided by n. So I say if you sum up all the zik's for one data point, you get a 1. And then you sum over, so you have to reverse the sum here. Sum over I of sum over k of zik, 1 n in front of it. So now, this last sum is 1, right? Because the sum of probabilities over the cluster for one data point is 1. Therefore, now this is n by n. Good. We have this. Now, of course, I skipped the interesting part, which is the next week math exercise, which is okay. Those make sense. But remember what we have to do? We have to write up some sort of likelihood or function, differentiate it. How do we get those formulas? I mean, they make sense, but we gotta at some point go over all this math and see why is that. All right, but for now we're gonna keep it like that. What's up with the other step? There's another step going on. I don't want to erase that. I'm gonna fit it somewhere in here. I don't know where. I'm gonna try to fit it in here. Cut half of this Gaussian. So that's my M step. How about the E step? So I took this step in here. What was the E step doing? The ZI case, right? So it has to compute these probabilities. Once you have the Gaussians, once I have the picture, the means and the variances, I have to figure out what is this, and what is that, right? So how do I do that?
The normal, Gaussian.
Or each normal divided by the sum of the normals.
Right, so the formula I have here ZIK, this probability, is the probability of xi let me write it nice. The normal of xi with mu k and sigma k. That probability, right? That is this portion. So I have three scores. I have these scores, I have this score, and I have this score, right? That's the three probabilities coming from the Gaussians. But I want them to sum to 1. Do they sum to 1 automatically in here? No. So what do I have to do? Normalize it, right? So this will be over the sum over all Gaussians that I have. So this E goes from 1 to k of the same thing. Xi mu t sigma t. So this is the Gaussian function. And what I have here, I have multiply with pi k. So why is that? Why when I do this normalization, I have to multiply with the pi's? Yes.
You have different weights on the normals, and you have to weight them and then average.
Right. But that's something we need to think about it for a little bit. Why is it that when I have these three scores in here, it's not the score divided by the sum of the scores. This is the same thing like with the prior in base. There was a prior there. How many points have y equals 0, right? Remember the base formula? The same thing in here. It's not just this probability, it's the probability adjusted by how many points have this kind of prior, or how many patients are of this class. Now, of course, this will still sum to 1. It's a normalization. Just every Gaussian is weighted by that. Is that corresponding to this formula I have here? The E step? Is it? That will correspond with this formula if I have the covariance matrices, which I didn't quite compute, right? This is a hard decision, like arg means says give me the Gaussian that's the closest, right? So it ends up with a 0, 1 output. This one here will not produce a 0, 1 output. It's gonna produce a soft, right? What's the corresponding Armax if I have those three distances? Which ZIK becomes 1 in the discrete case? The highest, but it's not the probability, it's probability times the pi, right? So it's the highest weighted by how many things on prior have that category on them. In here, I don't want to do that. So very specifically, soft k-means or Gaussian mixtures, I do not want to say hard 100% to one cluster, 0 to the others. I want to say if a point is here, it has maybe a 80% to be in this cluster, 15% to be in this cluster, and 5% be in the other cluster. So now I have this. This whole thing has a name, this procedure. Now we kind of copied the discrete formula for k-means, and we put them to work on the same data, so the x's are the same. There's no labels here. I'm just trying to fit a curve to data. The curve I fitted yesterday, the other day, was a Gaussian curve. In here I'm fitting a 3 Gaussian curve or a 5 Gaussian curves. What's the name of this procedure?
Expectation optimization.
So expectation maximization has this, it's applied in many problems where I don't want to take derivatives, set them to 0. I mean, I can, but that's too hard. So instead, I fix some of the parameters fixed and then optimize for the others. In this case, I'm going to keep at one point fix the parameters of the mixture and optimize the probabilities, the memberships. Or keep the membership fixed and redo the Gaussians. That mechanism is very similar to k-means. The memberships, when the memberships are fixed, even though they are probabilistic in my problem here, I recompute the Gaussians, which is the centroids. They don't just have means, they have means and variance and a mixture between them, which is the size of the clusters. That is it in this step. If the membership is fixed, I can recompute the centroids, the variances and all that. And backwards, if this is fixed, if I have the centroids and the clusters, I can compute who belongs to one cluster with what probability here. And the idea is that by doing this iteratively, running over E and M steps, just like I did it here, right? E step, M step, E step, M step, like I did k-means. At some point, I'm going to notice convergence. So I need to have a stopping criteria of convergence. When do I stop? When do I believe it's kind of stabilized? At that point, I say, if we didn't get unlucky to get in a local optima, suppose we got to a global optima, where we want to be, I say I managed to fit a k-Gaussian curve mixture to my data. The benefit being a k-Gaussian mixture may fit much better than one Gaussian. Yes?
The previously we had done one version for the positive, one version for the negative.
In here we'll do the same. We'll have to fix a mixture for the positive side, a mixture for the negative side, and then see which one, then at test time, see which mixture gives me the higher probability. But this principle is in general. Just remember, if you want to fit a Gaussian to data, GDA is not the only application for that. Often you want to fit a curve to data. Instead of going for other curves, like beta distributions, might be easier to fit a 2 Gaussian, especially if you know, you have some domain knowledge about the nature of the data. So a doctor might know there are 2 main types of patients, that type and that type. And then that kind of calls itself for a 2 Gaussian mixture, right? Because I'm expecting to see a lot of patients of that kind, a lot of patients of that kind, but maybe not that many in between, so then I can fit a 2 Gaussian mixture. So what we want to do is, there may be some exercises with EM, and this is a GDA exercise, there's an ID-based exercise, and some things with EM, where you can do the fitting and then use the same like in GDA, apply it, do separate classes fitting, and then do the testing on it. What's left here is to figure out where those formulas are coming from. For that, I'm going to do the same like I kind of watched it last time in class, right? I'm going to do the same. I'm going to try to do some of it in class, and then we let the people who are mathematicians figure it out, write it nicely, put it on Piazza for everybody to see. Okay? Because I don't want to make this a math class, but if you are interested, we can definitely spend the time to figure this out. This looks very, very, makes a lot of sense, right? these formulas, you can see the analogy, I think make total sense why they work for not 0, 1, but probabilistic versions. So I have some derivations for why that is. That's gonna happen. All right. So we have a long weekend ahead, but I don't think we can, since the deadline for the homework 3, the neural networks, it's already pushed through. I think you guys could have finished by tomorrow. So it's by Tuesday. I don't think we can push that much. So I'm going to release our next homework that's EM and GDA and naive Bayes. But you guys can't take forever to finish the neural networks, okay? How many people have done at least the first 2 networks, not the maximum likelihood? Your hands up. Have them working somehow? Almost working? Have a plan to make them work? All right. I'll be at open hours today. I have to stop the camera.
There's only 2 I think this is the summer. The means getting this summer. Actually, yeah, because I don't want to. I want other subjects. I don't take
That's the concept. In reality, you just go Yeah, I also don't have it for more than 50 minutes, but I think the integrals under the math will want.
Okay, great, thank you. So, okay, see you back.